Hi, in this lab, I'm going to go over Lab 4, which is an experiment about the experimental and computational applications of Faraday's law. Um, in this lab, we're going to collect observational data of a magnet falling through a tube of aluminum foil, and we're going to compare that to a computational model of this interaction. This is the main equation we're going to be using throughout the experiment. This is Faraday's law, which states that the change in magnetic flux, the negative change of magnetic flux, is equal to the time derivative of the integral of the magnetic field times the area. So the procedure, and quick overview of the procedure is we're going to mark the north pole of the bar magnet, and we are going to position the bar just above the top opening of the aluminum foil, and we are going to drop the magnet through the top opening, and we are going to note the time when the magnet enters the loop and exits the bottom of the loop, and we found that this time was slower than what would be regularly expected due to solely the force of gravity. And after this, we repeat the experiment 5 times and find the average time. Here are the parameters we used for the aluminum foil and the radius of the tube. The radius of the tube is the particularly important part, and the width and the length are because this defines our area that the flux encompasses. And we found that the average fall time for our bar magnet was 1.27 seconds. Plugging these parameters into our computational model and adding the necessary equations, we found that the fall time from the computational model was 1.19 seconds, which is pretty close to the average fall time over the experimental part. This was our velocity versus time graph. We found that through the fact that the magnetic field increases while going down, the red current, which was on the bottom current ring in our computational model, would have to be counterclockwise to abort the increase in magnetic field, because due to Faraday's law, the induced magnetic field and the induced current is always going to try and resist the force of the magnetic field. When you flip the magnet around, the time it takes will stay the same due to the fact that the area is still the same and the magnitude of the magnetic field is the same. However, the magnetic rings swap directions. So this time red was on top and blue was on the bottom, so the induced magnetic field also changed direction. Causes that may have caused a difference between our computational and experimental model is that we assumed air resistance was 0 in our experimental model, and we may have needed more trials to get a more accurate and robust figure for the time it took. And looking at this velocity versus time plot, we know that the magnetic force equals a gravitational force at terminal velocity, or when velocity is constant. This means that there's no net force on the system between about timestamp 0.1 and 1.1. And after that and before these two markers, there is a great difference between the two forces of gravity and magnetism. If the resistivity of the conductor was close to 0, the magnet would fall at a much slower pace because current is inversely proportional to resistance, so the current would increase, and this means that the counteracting force to the magnetic force would be a lot higher, slowing down the magnet. And the flip side of this scenario is if holes were cut into the tube, which would decrease the current of the rings, making the counteracting force weaker and the magnet to be able to fall a lot faster. Thank you.